Hello, everybody. It's my pleasure to introduce Professor Bjorndal. He's one of the most important researchers in fisheries and aquaculture economics, where some of his experience, I will try to summarize it. So he has been a professor at the Norwegian School of Economics and Business, also at the University of British Columbia, at Simon Fraser University, and several others. And right now, he's the director of the Center of Economics and Management of Aquatic Resources at the University of Portsmouth in the UK. Also, he's a former chairman of the World Fish Center, was the president of the International Institute of Fisheries, Economics and Trade. He has also been a guest or associate editor of many journals and has been a consultant to the FAO, the OECD, the Exxon Corporation, the Seafood Export Council of Norway, and several government ministries. He has also published extensively in journals on topics such as open access and optimal management of fish stocks, the production function in fisheries and aquaculture, cost and productivity analysis in fishing, processing, and aquaculture, as well as market analysis for fish and fish products. He has also written several textbooks on fisheries and aquaculture as well. So please receive Dr. Bjorndal and the talk called Aquaculture Development and Environmental Sustainability.
Thank you. So good morning, everybody. I'm delighted to have been invited to the University of California, Santa Barbara, and to the Bren School. And this morning I will be talking about aquaculture, and then in the afternoon I will give a lecture also to the fisheries group. So, as you know, aquaculture is a production process that is carried out in water and therefore impacting the environment. The increase in global aquaculture and the introduction of intensive farming practices in particular has led to both global and local environmental concerns. The main global concern is that increased demand for feed from a growing aquaculture sector will increase fishing pressure on wild stocks and consequently threaten the sustainability of the associated capture fisheries, since marine proteins are important ingredients in the diet for cultured seafood. This is what is known as the fish meal trap. And according to the fish meal trap hypothesis, which was postulated by Wikström of the FAO and Naylor et al. In a Science article, growth in aquaculture production increases demand for forage fish to produce feed. This makes aquaculture production inherently unsustainable and environmentally degrading. Now, for this to be the case, it requires that forage fisheries are poorly managed, that forage fish has no substitutes, and that cost is not important for aquaculture production. And second, eventually this will put a limit on aquaculture production. For this to be the case, it requires that aquaculture feed must contain marine ingredients. More local concerns include discharges from farming sites, destruction of local habitat, and spreading of pathogens. So, the lecture outline is as follows. First, I'm going to talk about the fish meal trap, other limits to growth for aquaculture, and I will in particular look at fish meal production and resource management, and also at the market for fish meal. I'm also going to talk a little bit about local environmental issues with examples from salmon aquaculture in Norway. To what extent the fish meal trap represents an environmental problem depends on whether increased aquaculture production actually increases fishing effort on species that are used for production of fish meal and fish oil. This in turn depends on First, does the fishery management system allow increasing fish meal demand to translate into fishing effort and catches? Second, to what extent are there substitutes for fish meal so that buyers will reduce demand if the price increases and purchase more of alternative meals? This figure shows estimated total use of fish meal in 2008. The share of fish meal that is used for aquaculture purposes has increased from essentially zero in 1980 to a share of 59% in 2008. Other main users include poultry production and pork production. If fish meal is part of a larger protein meal market, increased production will not result primarily in increased demand for fish meal, but rather increased demand for protein meals, of which vegetable meals account for the majority, probably 95% of total production, mainly soybean meal. Further, if fish meal is not an essential ingredient in the fish feed, higher prices of fish meal will lead feed producers to substitute away from fish meal. So, on to fisheries management. Reduction fisheries are mainly based on fisheries for pelagic species. These species are used both for human consumption and for reduction into fish meal and fish oil, but certain species are mainly, or at least, and in some cases only, fit for reduction processes. This slide gives the global production of fish meal by source from 2000 to 2009. You notice in 2000 a production of 7 million tons, in 2009 a production of slightly less than 5 million tons. Fish meal is used or produced from whole fish, but it can also be used from trimmings, from byproducts, and from what is called trash fish. And what we do know is that the production from trimmings, from byproducts, has been increasing, and by 2020 is expected to reach 2 million tons, while on the whole, production from whole fish has been declining over time. This slide gives world fish meal production by major producing country up to 2011. And what you notice is, of course, that Peru is the #1 producer. Thailand is a big producer. So is Chile. The US is a smaller producer. Then we have Japan, Scandinavia, and then the rest. There are important variations from year to year. I will come back to that in a little while. This gives fish oil production by country for the same period. And you notice, again, variations from year to year. On average, the production of fish oil is about 1 million tons per year. Sorry. A characteristic of pelagic fisheries is that while the quantity for human consumption stays relatively stable, the surplus, which is used for reduction purposes, can vary dramatically from year to year. Thus, in years when the catches are low, such as in El Niño periods, the fish meal industry is hard struck. An increase in fish meal production can happen in 3 ways. First, by increasing catches due to increased fishing effort, if the management system allows it. Second, by diverting landings that are now used for human consumption, or by increasing the use of cut-offs from fish processing and byproducts. I already talked about the expected production in fish meal from byproducts over the next decade. To show you some examples of fish meal production, this slide shows total Norwegian landings and the share used for reduction into fish meal and fish oil. Oh, sorry. Sorry, I'm not terribly. Sorry. No. Thank you. Thank you. I only learned to use a PowerPoint 2 years ago. Thanks to a good assistant. Anyhow, so this slide shows it shows Norwegian landings. This curve here from 1977, 3.3 million tons, came down to 1991, increased, and let's say on average about 2.5 million tons per year. A dramatic increase, the dramatic change here is in terms of the share that is used for fish meal. In 1977, this was close to 75%. In the last few years, it has been reduced to only 30%. Now, why is that happening? We can look at this curve for Norwegian spring spawning herring. Back in the 60s, the largest share of herring was used for reduction into fish meal and fish oil. Over time, this has changed, and it is now mainly used for direct human consumption. Why is that? Well, it is, at least to a large degree, explained by the price. This is the price for deliveries to human consumption. This is the price for delivery to meal production. And you notice that the price fetched for human consumption deliveries is substantially higher. Fisheries management regimes can in general be divided into three main groups. One is open access, the other is optimal management, or what we would call sole owner management, and the third one is restricted open access. I would say that most fisheries nowadays would fall into category 2 or 3, or perhaps mainly category, well, a combination of 2 and 3. So the extent to which increased demand will increase fishing pressure depends on the management regime. In the case of optimal management, the size of the landings may respond to increased prices. However, there is little danger of over-exploitation, since sustainability is a main concern. It is also a main constraint on the system. In open access fisheries, the competitive behavior of fishermen will lead to overexploitation of fish stocks, and in some cases even to stock extinction. If we go back to the herring case, you notice that very low catches here, 88, 89, 90. Why was that? The fishery, the stock was driven to near extinction in the 1960s due to an open access regime. It took 26 years for the stock to recover. It has actually recovered, and this is now an example of a sustainable fishery. If you're interested in this fishery, come and listen to me at 2 o'clock, and I can tell you the full story about it. So open access will lead to overexploitation and in some cases to stock extinction. This situation will be exacerbated by increased demand, as the higher prices will lead to higher effort. Higher prices mean more profitable fishery, more fishing effort, even if the stock declines. And this issue is particularly problematic for pelagic fish stocks, where harvesting costs are not very sensitive to stock size. So the real problem with respect to the fish meal trap is with open access, or when management is weak, so that regulations are not enforced as these are the only scenarios where increased demand will lead to an increased fishing pressure and increase the risk of serious stock depletion or even stock extinction. So what is the case then for some of the important stocks used in these fisheries? I've listed some stocks here. I've listed some characteristics. I have listed, given some keywords with respect to management system. Peruvian anchoveta, we can say it is a very vulnerable fishery, and it is highly variable, in particular due to the El Nino. Fisheries management has improved over time with the introduction of total allowable catch quotas and improved or stricter input regulations. This is the largest fishery in the world, and there was a time when fishing capacity was so high that the total quota could be taken in less than a month. You can imagine the excess capacity that was involved in this fishery. But the situation has been getting better. Chilean jack mackerel, we had a discussion about that this morning. They do have TACs, they do have ITQs. We can discuss how effective they are, but certainly management has improved. I talked about herring. It is now a sustainable fishery. It is a shared fishery, it's a shared stock, and we have TACs with individual vessel quotas or individual transferable quotas. Two other fish stocks in the North Atlantic, mackerel and blue whiting, potentially unsustainable due to the straddling nature of the stocks. It has nothing to do with the fish meal trap or the demand for fish meal production. Unsustainability is due to, let's say, the sharing of the resource on the high seas. And this fishery in the United States, I'm sure people in the audience know it better than me, so I won't comment on that. Open access is not an appropriate description of the management situation for most important pelagic species. However, quotas tend to be high, and one may often question whether sustainability has been the main criterion when setting quotas. Therefore, whether increased demand for fish meal will lead to unsustainable fisheries will also to some extent depend on the market structure for fish meal. So now on to the markets for fish meal. There are two main reasons why fish meal is used in livestock as well as aquaculture production. The first one is what we could call the possible uniqueness of fish meal. There used to be what they call an unidentified growth factor. When they looked at how livestock and fish grow, there was a factor they could not identify, but they associated with the use of fish meal. So basically, one reason is that fish meal is supposed to have some unique characteristics when it comes to growth of fish and growth of livestock. The other is that in general fish meal is a cheap protein. Now these cases will give very different implications for what kind of market we are dealing with. If fish meal is used because it is unique, the price of fish meal would be determined by the demand for and supply of fish meal alone. So basically you have a separate market for fish meal. If in addition fish meal is essential in the aquaculture food, then increased demand for aquaculture can drive demand for fish meal. However, if fish meal is a close substitute for other protein meals, the price is determined by the total demand for protein meals. If so, increased demand from aquaculture is not a threat to wild stocks. So basically, the question is, what is the market? This figure shows monthly fish meal and soybean meal prices from Hamburg from 1980 to 2008. I tried to update this. I received some very recent price data as late as yesterday, but I have not been able to update this figure. First of all, what you notice is that the fish meal price is higher than the soya meal price. That is simply because fish meal has a higher protein content than soya meal. So that's the reason for that. What we have to keep in mind is that the period here covers some extreme situations for fish meal production due to low raw material supply, because the period covers several El Niños which had a big impact on the production. However, we cannot see any impact of the El Niños up to, let's say, year 2000. Second, this period, the 1980s and the 1990s, covers the period when the growth in intensive aquaculture production has taken place. If fish meal is primarily demanded due to its special attributes, this would identify fish meal and soya meal as different market segments during the period. Results by Asche and Tveterås suggest that fish meal and fish oil are very strong substitutes. Therefore, until 1999, it appears that total demand for protein meals that Therefore, it appears that until 1999, it was the total demand for protein meals that determined the price of these protein meals. In order for aquaculture to influence the price of fish meal with this market structure, the changes in demand or supply must be large enough to affect demand and supply for fish meal, for fish and soya meal combined. With this market structure, it seems unlikely that increased demand for fish meal from the aquaculture sector will increase fishing pressure in industrial fisheries. However, the figure also indicates that the relationship becomes wider after the turn of the century, and there are indications that a structural break has taken place. We notice that the price of fish meal skyrocketed in 2006, indicating that fish meal to a larger extent became demanded primarily because of its unique attributes and accordingly is not part of a larger protein meal market. However, the soya meal price increased with a 1-year lag, and the prices were to a considerable degree realigned in 2008. This table shows world fish meal and fish oil consumption compared to the growth in fed aquaculture from 2000 to 2010. Yes. Let me try. Not quite, no. Left, right? Yeah, no.
You want to go back to full screen?
Yes, please. Thank you. On the left-hand vertical axis, we measured aquaculture production, which increased from about 15 million tons in 2000 to more than 30,000 tons in 2010. That is more than a doubling in 1 decade. And remember, this is what is called fed aquaculture. That is aquaculture that is based on the fish being fed. Then we have here fish meal in aquaculture, and quantities are measured on the right-hand vertical axis, and the quantity increased from about 2.25 million tons in 2000 up to about 3.3 million tons in 2009, and then it declined to a level of slightly more than 3 million tons in 2010. Fish oil, on the other hand, increased from 0.75 million tons in 2000 to about 0.85 million tons in 2007, and then declined to less than 0.7 million tons in 2010. So what we see here is that growth in global aquaculture production does not lead to increased use of marine ingredients, or at least it leads to this only to a limited extent. It seems likely that the growth in aquaculture production is fairly independent of the cycles in fish meal prices and of the availability of fish meal. As one can see, there is a very strong growth in total aquaculture production, as has been the case for salmon. Hence, the cycles in fish meal price do not seem to have a strong impact on aquaculture. For most aquaculture species, fish meal does not seem to be an essential ingredient. However, to the extent that there are species that require sufficient quantities of fish meal, producers of these species will find that feed costs will become more volatile, and if the price continues to increase, it may be a problem for the profitability of the operation. So, as I've already said, the most important fish stocks used in fish meal production are managed with quota systems, although one can question if these are sufficiently comprehensive to prevent the fish meal trap. Whether fish meal is demanded from aquaculture because of its unique properties is less clear. If fish meal is close substitute to soya meal, it is the total supply of and demand for protein meals that determines prices for fish meal. The growth in aquaculture has not been much influenced by fish meal prices, and one seems to be able to substitute away from fish meal when prices are high. One is then led to the conclusion that increased demand for fish meal from aquaculture cannot have any significant impact on fish meal prices in the long run, and accordingly does not lead to increased fishing pressure. It is a fact that demand for fish meal from aquaculture has grown from zero, or virtually zero, to more than half of total production in only 20 years. If the demand for fish meal continues to grow, it is possible that this structure may change. However, this does not have to be the case, since it is not clear that the demand for fish meal from aquaculture is mainly due to the unique characteristics of fish meal. Moreover, productivity growth leading to lower cost of production has been a main factor in the growth of the salmon aquaculture industry, and this is the case also for other species. If the market structure changes so that fish meal is demanded because of its unique characteristics, production costs will also increase and therefore limit the demand for feed from aquaculture. Hence, even with a structural change in the fish meal market, the increase in demand from aquaculture and feed prices are likely to be limited. Some commentators indicate that lack of fish meal eventually will prevent further growth in aquaculture production. For this to be the case, fish meal must be an essential input. As this does not seem to be the case for most species, this concern seems unjustified. So, in conclusion, the fish meal trap hypothesis makes for a good story, but it does not appear to be borne out by the facts. On to local environmental issues. Any production process that interacts with the natural environment has the potential to damage the environment around the production site, such as destruction of natural habitat and pollution from production. For salmon farming, the main issues have been pollution from organic waste and the interaction between wild and farmed salmon. Shrimp farming has received negative publicity due to detrimental environmental effects, such as destruction of mangroves, saltification of agricultural areas, eutrophication, and disruptive socio-economic impacts. The environmental issues that arose in intensive salmon and shrimp farming during the 1980s and 1990s must be seen in relation to the introduction of a new technology that uses the environment as an input. The larger the production at any site and the more intensive the process, the larger the potential for environmental damage. However, the greater the degree of control with the production process in intensive aquaculture production also makes it easier to address these issues. Petros, 2002, argues that industry growth can have a positive effect on pollution in line with the environmental Kuznets curve. The EKC hypothesis refers to an empirical observation that pollution tends to increase with economic growth up to a certain level, after which it will reduce pollution. This gives the pollution profile over time the shape of an inverted U. There are three main causes, or three main reasons for the industry to address environmental issues. The first one is that the effects will reduce productivity and therefore profits, and/or government regulations force the industry to do so, and/or increasingly consumer pressure. Detrimental environmental effects of aquaculture not accounted for in market prices are by definition negative externalities. Asche, Guttormsen, and Tveterås from 1999 argued that internalization of externalities explains why some of the major environmental issues have been resolved in salmon aquaculture. Fish farms with environmental practices that cause the quality of the local environment to deteriorate will experience negative feedback effects. Consequently, one is concerned with developing management practices that avoid such negative repercussions on productivity. If there is no such negative feedbacks, however, it is unlikely that the industry will internalize these effects, and in this case, the government is called on to regulate the industry. I'm going to look at some of the environmental issues related to salmon aquaculture, and I'm starting with organic waste. Effluent discharges are one of the most important environmental concerns in salmon farming and account for most of the pollution around fish farms. The organic waste can build up on the seabed if the rate of decomposition is sufficiently low, thereby damaging the local fauna. Another problem is that waste leads to higher concentrations of nutrients in the sea, which increases the risk of eutrophication. However, eutrophication depends on the nutrients being discharged and on the resilience of the local environment. A strong current increases the availability of oxygen, which is needed for the decomposition of the organic matter, and also contributes to a wider dispersion of it. Hence, the organic load directly under the cages is reduced, thereby alleviating the challenge to the environmental resilience capacity. Since seabed topography also influences the resilience of the environment, the siting of cages is important. Most farms nowadays are located in areas with relatively strong currents. They have been moved from the fjord areas to much more exposed areas, in areas with deep water and suitable seabed topography. This significantly reduces the accumulation of waste sediments and negative feedbacks on productivity. Organic waste sedimentation not only poses a problem for the local fauna, but also for salmon farmers due to negative feedback effects on productivity. This production risk increases with higher feed use because of the negative environmental feedback. Therefore, risk-averse farmers would minimize feed use and or take other measures to reduce negative feedbacks on productivity. As feed cost may amount to more than 50% of total cost of production, there is also a cost argument for reducing feed use. This figure shows the feed conversion rate and Norwegian salmon production from 1980 to 2008. This line shows production increasing from virtually zero in 2000 to more than 800,000 tons in 2008. The vertical bars represent the feed conversion ratio, basically the amount of feed that is used per kilogram of salmon produced. I said there might be an inverse relationship, or we might have an environmental Kutzler's curve. What we see here is that in 1980, 2.8 kilogram of feed was used per kilogram of salmon produced. This has come down over time, and by 1995 it was down to about 1.2. We don't have the inverse U-curve here. Why is that? Well, the main reason for that is we do not have any data points prior to 1980. But we do notice that feed consumption has come down quite considerably in this time period. It has come down for many reasons. One reason is increased use of lipids in the feed that has caused a reduction in organic waste. Also, new feeding systems have contributed to reducing the food conversion ratio by lowering feed waste. So it is a combination of new cage technology, which allows sites to be moved to more exposed locations, rotation between sites, and improved feed and feeding technology that has significantly increased the elasticity of substitution between traditional factors of production and effluent discharges. This has probably been induced by a combination of environmental feedback effects on productivity and a general effort to reduce costs. Consequently, salmon farmers have internalized many of the problems relating to organic waste. In this context, it is important to note that the improvements in the feed and feeding regimes have to a large degree been made by the feed industry. Then on to antibiotics and the use of chemicals. The use of antibiotics in the treatment of diseases is a controversial issue concerning the environmental practices of salmon farmers. Antibiotic use can lead to antibiotic resistance in fish and other living organisms. In particular, the extensive use of antibiotics in the late 1980s provoked much criticism from consumers. So this curve shows the use of antibiotics in fish, salmon in Norway, and fish production from 1974 up to the present. And here you see an inverse relationship between use of antibiotics and fish production. Use of antibiotics increased rapidly here up until the end of the 80s. It came down and then increased again. And then since the early or the mid-1990s, it has virtually been eliminated. What were the reasons for this? Well, there was outbreak of a disease called vibriosis in 1986, and then we had tuberculosis in 1992, which led to the excessive use of antibiotics. Why has it come down? Well, for two reasons. One, as already mentioned, relocation of farms to more suitable locations, which generally has improved fish health. And second, the introduction of vaccines in 1992, which was effective against bacterial diseases and which made use of antibiotics largely redundant. I mentioned the importance of the feed industry when it came to reducing feed waste, and the development of the oil-based vaccine can also be seen as the result of an industry becoming more attractive to industry-specific pharmacy services and products. Thus, industry growth has helped to reduce the use of antibiotics, not only in relative terms, but also in absolute terms. This is the use of, shows the use of chemicals in salmon production. Why are chemicals used? For two reasons. One is to clean the nets, and the other is to try to reduce the impact of sea lice. Wrasses, small kind of fish, has been introduced as a more environmentally friendly method of treating sea lice because they feed on sea lice that live on salmon. However, on its own, it is not sufficient to eliminate the sea lice. Nevertheless, what you see here is again an inverse relationship, or a rather inverse U-curve here. Use of chemicals increasing up to 1985, and then dropping quite dramatically to 1987, and then coming down and stabilizing at a fairly moderate level from the end of the 1990s. salmon escapees and sea lice. Now, the issue of salmon escapees is very controversial because of its potential negative impact on wild salmon stocks. This is a very up-to-date figure. It shows escapees of farmed salmon and rainbow trout from 1993 to including last year with preliminary figures. High level here in 1994, coming down in 95, increasing again, coming down again, increasing to even higher levels. Then in the last 5 years, we notice low level in 2008, higher level 09, 10, and 11, and then coming down again in the last year. We don't see the same nice inverse U curves as we saw for organic waste and antibiotics. Sorry. And I would say, to some degree, let's say, the jury is still out on this account. I would hope that the 2012 figure is also something we will observe in coming years, but again, it is a little bit too soon to tell. I think these figures should be treated with some caution because they are probably lower than the actual number of escapees for several reasons. Escapees can generate negative publicity and lead to lawsuits, which gives a reason for underreporting. However, farmers may also be unaware of escapes because damage to cages is detected late. However, underreporting is not likely to affect the main trend that we have seen. Infection by sea lice is possibly an important factor in the reduction in the wild stocks in salmon-producing regions. Registrations show that the heaviest infections of wild salmon are limited to areas with a high concentration of salmon farms. A plausible explanation is that the number of hosts is larger in areas with high concentration of salmon farms, thus leading to a higher concentration of sea lice in that area. Moreover, escaped salmon are believed to be one of the major causes of spreading salmon lice to wild salmon. Sea lice infections and salmon escapes are probably the major remaining environmental problems in salmon farming today. Salmon farmers clearly have an incentive to limit the amount of sea lice because of negative feedback effects on productivity and also for marketing purposes. However, it is not clear that salmon farmers have an incentive to reduce the number of sea lice to a level that is significantly below the level required by the market. This means that sea lice concentrations in salmon farming areas might be relatively high, even if the number of sea lice living on the farm salmon is at an acceptable level. Thus, it is uncertain whether there has been an inverted U-shaped pattern for the level of sea lice in salmon farming areas. Research on vaccines against sea lice continues, but there has been no major breakthrough to date. Large-scale aquaculture has the potential to severely impact its local and regional environment. However, the control with the production process that makes large-scale intensive production possible can also be used with respect to environmental matters. As an issue has to arise before it can be addressed, it can take some time before one is able to respond. In the case of Norwegian aquaculture, the environmental issues have to a large extent been addressed. This is partly because the negative environmental influences also have a negative impact on cost of production, and partly because of regulations. The state of environmental practices for salmon should hold an important lesson also for other species. With a sufficient degree of control with the production process, all environmental issues can be resolved, and salmon aquaculture is certainly sustainable. It will not necessarily be the case that the industry will have incentives to internalize all environmental issues, and as such, there is an important role for regulatory authorities. However, to the extent that aquaculture is carried out in an unsustainable manner, it is not because it is intrinsically unsustainable. It is rather because authorities are not able or willing to implement and enforce regulations that make the producer use the best practices available. Thank you for your attention. If you have any questions, I would like you to turn your attention to this book, The Economics of Salmon Aquaculture, published in April 2011. Thank you.
We have 5 minutes. Do you want to take a few
Sure, yes.
We got like 5 or 6 minutes, so if anyone wants to, if anyone has questions, go for it.
Please.
Among forces that might help make it sustainable, is there a strong role for like consumer pressure that you mentioned, like for instance the Munro aquariums in West Risk?
Yes. Sorry. Yes, very much so. And definitely when talking about antibiotics and diseases, that was very, very much the case. And it caused enormous negative publicity, I would say, in many, many countries. And I have recently been doing work on what we call value chains in fisheries and aquaculture in general, looking at, let's say, the production of fish from aquaculture and from wild stocks in different parts of the world, and their contribution to future food security, and let's say the impact of the consumer is, I should say, growing almost by the day. Yes. Yes.
You showed, I thought, a lot of really encouraging data about the impacts on local ecosystems for Norway. Could you say that, at least for salmon worldwide, the picture is pretty similar? Like in New Zealand and British Columbia and Chile?
Well, we have an expert from Chile, so perhaps I should defer to him. But I guess the main point is, I guess 2 points. Chile has been different from Norway, in particular in terms of their environmental practices. Their environmental practices have been very different. They have been through a very, very difficult period. And the question now is if they have learned the right lessons. Time will show. Time will show. But there is no reason, as I said, why salmon aquaculture should not be sustainable. Yes, please.
Yeah, my question is sort of the same. What brings these lessons from Norwegian salmon fishery applied to other fisheries and other aquaculture? And so the issue is shrimp farming.
Yes.
And so it's a little hard to see how that's sustainable because of the habitat destruction that occurs up front. And with regulation, you can't have the shrimp aquacultural industry. So I don't quite understand how this can be a lesson for that industry, how that industry can be sustainable.
So why is it not a lesson?
Because the initial habitat degradation has already destroyed the environment that you're raising the shrimp in. So
Well, as I said, there are three ways of dealing with these problems, and one that I started out with is that these issues are internalized. Now, why are they internalized? Why have they been internalized in Norway? A major reason for that is that the number of sites has been limited. So if you basically destroy the habitat around your farm, you are out of business. And that gives you a very strong incentive. Where that is not the case, where you're allowed to destroy a habitat and move on to a new habitat, and then of course you don't have that incentive. And that means that there is basically a breakdown in zoning restrictions and use of the coastal zone. Another issue, of course, the second issue I mentioned is with respect to government regulation. I mean, first of all, you need to understand that there is a problem. You have to find a solution. You have to impose, not only impose restrictions or regulations, you also have to enforce them. And of course, you're not able to do this in very many countries. And then we're left with the third, pressure, namely the force of consumers to have an impact on that. So I believe I'm more optimistic than you, based on the way you phrased your question. I have a positive view. I believe over time the kind of problems you mentioned for shrimp aquaculture will hopefully be reduced. Yes? Yes, please.
Has there been a change in the composition of the feed for salmon because you saw such a large increase in production?
Yes, yes, yes. Let's say this, I think there are two factors. Well, there are many factors. Of course, salmon production has increased, which means you need much more feed. However, let's say fish meal as a sort of a share has come down, okay? And that, of course, means that you could expand much more than otherwise. So only last week I was at a meeting in the Netherlands, and a person was talking about feed for turbot. And he said he was a biologist, he had varied the intake of fish meal from 53% to 93% of the feed. And he said including less fish meal had caused a reduction in the overall feed cost. So it was beneficial from that perspective. I asked him if they had tested the taste, if it had an impact on the taste of the fish, and he claimed it did not.